Water has to be one of the most important molecules in the atmosphere. Water can occur, of course, in three different phases. Just going over them quickly, water is generally in liquid form. 98% of the Earth's water is liquid. However, water can also be solid, which is it's below the freezing point, 0 degrees Celsius, and becomes hard in the form of either ice, snow, or hail. Then the third phase is gas, also known as water vapor. This is the least amount of water is in the form of water vapor. Now, water vapor, also known as steam, is actually not visible to the naked eye. We cannot see water vapor. If you have a pot of boiling water and you see this big cloud, what you're seeing is steam that is actually recondensing to form a small cloud on top of your pot. Water vapor is a contributor to the greenhouse effect and is one of the principal causes for weathering and erosion in geology. But even though it has to do with the greenhouse effect and the weathering and erosion, water is absolutely critical. About 70% of the Earth's surface is made of water, and more than 60% of the human body is made of water. It's probably, if I remember right, that percentage is actually much higher. You can see that in a biology text somewhere. But you can see how important water is both to the world and to our individual lives. Now, when we talk about humidity of the atmosphere, we look at a comparison of evaporation and condensation. Evaporation is the change from liquid to gas, and condensation is the change from gas to liquid. Now, we're always told that the evaporation point is at 100 degrees Celsius, 212 degrees Fahrenheit. But really, this liquid to gas, gas to liquid phase change can occur at any temperature. Now, we can say this because of what temperature really is. When we look at the definition of temperature, really, temperature is nothing more than a measure of kinetic energy. Now, recall from our physics that kinetic energy is a measure of the energy of the motion of an object. So when we talk temperature, we're talking about a measure of the motion of molecules. So really, any temperature, if a molecule has enough kinetic energy, it can separate from the liquid and it flies off on its own, becoming a gas. Now, if the liquid molecules have more kinetic energy than the average kinetic energy of the water, then it evaporates. In other words, it flies out, which is indicated by these red lines, red arrows in these figures. However, if the gas molecules have less energy than the average kinetic energy of the liquid water, then it condenses. It reverses and goes back from gas to liquid, indicated by the blue arrows. Now, quick note about saturation, pardon me. Saturation is the equilibrium between evaporation and condensation. Consider this first picture. You have, for every one molecule that is condensing, you have 3 molecules that are evaporating. So you're going to have more evaporation than condensation. If you were to watch this cup of water over time, the water level would drop. Now, and that's why we say evaporation, because the water is primarily evaporating away. But if you have for every one molecule that's evaporating, you have 3 molecules that are condensing, you have more water that is condensing into the cup, your water level should rise. So you have a net condensation. But if it's perfectly balanced, for every one molecule that evaporates, you have 1 molecule that condenses. It's perfectly balanced. There's not going to be any change in the water level. This is saturation. In other words, what happens at saturation the air is holding as much water as it possibly can. So if you have one water molecule evaporate, the air says, hey, I've got enough. I can't hold any more. So it sends one molecule down, condenses back into the jar. That is saturation. The saturation point is influenced by temperature. If the temperature is higher, in other words, warmer air, you can hold more water vapor. Colder air temperatures mean you can't hold as much water vapor. So humidity is the measure of how much water is in the air. Now there are multiple ways to measure this, but the two primary ones that you need to be worried about are absolute humidity and relative humidity. Absolute humidity is an actual measurement of how much the mass of the water in the air. Now, the range of absolute humidity can be from anywhere from nearly nothing, nearly zero water, 0 grams per cubic meter. Let me say that again. It can range from near zero, meaning nearly 0 grams of water per cubic meter of air, and it ranges from 0 to the saturation limit. So, and the saturation limit depends on temperature. Let's say that the temperature outside is 20 degrees. This graph is then going to show the saturation limit. So the saturation limit here is indicated by this line where the blue line intersects the 20 degree Celsius line. That's somewhere around 018. In other words, the air at 20 degrees Celsius can hold anywhere between 0 grams per cubic meter and 18 grams per cubic meter. We can have any amount of water when the outside temperature is 20 degrees Celsius, between 0 and 18. So relative humidity is a relationship between the absolute humidity and the maximum possible absolute humidity, in other words, the saturation limit. So let's just say, for instance, that the absolute humidity is 6 grams per cubic meter and the outside temperature is 20 degrees Celsius. Well, relative humidity is going to be the absolute humidity divided by the saturation limit. In other words, we currently have 6 grams per cubic meter, but we can hold 18. Now, if you deal with fractions, that reduces to 1/3. That means that the humidity outside is 33.3%, because that is the same thing as 1/3. So that's how you do relative humidity. Just take the absolute humidity, the amount of water in the air, and divide it by the saturation limit at that temperature. And you're done.